Hello everyone. Thank you for joining us here today. So today we have with us Professor Manoj Gopalkrishnan from Electrical Department, IIT Bombay. He works in the field of algorithm design and learning systems from the study of self-organization. A multi-institute research team led by the Indian Institute of Technology Bombay has developed a new testing protocol called Tapestry. Tapestry is a mathematical algorithm for smart pooling of samples for COVID testing. The algorithm describes a novel way to pool samples and test in a single step, thereby conserving resources and increasing testing capacity by um, effective solution. So I would be handing over now to Professor Manoj. And if you have any questions, do post them in the chat box. So we'll discuss the relevant questions at the end of the talk. Another thing, we are also live streaming this on YouTube. So if you're having any issues with Zoom, you can join us on YouTube. Yes, Professor, you can continue.
Hi Latika, thank you very much for the invitation.
I think you're on mute, sir.
No, I am not on mute. I think my voice. Yeah, so I was saying thank you very much for the invitation. Very happy to be here. I think you need to enable screen sharing. That's what it's saying. So I can start. Yeah, but very glad to see so many people interested in this. And yeah, as soon as I can share my screen, I think I can start.
Yes, sir. Can you check now?
Yeah, I got it. So I'll just. Can you see the full slides on full screen?
Yes, I can. If anybody has any issues, do post them in the chat box.
Okay. So as Latika mentioned, so this work started at IIT Bombay, and then because at that point many of our students were away and we didn't have facilities to test, we got into collaborations with a bunch of other institutes, INSTEM and NCBS at Bangalore, BS Institute at Harvard in Boston, and now this has become a very cross-institute collaboration. Okay, so what's the story? We are all living through lockdown. We all know that the reason we are in lockdown is because COVID-19 carriers can be asymptomatic for many days. And so long as somebody is not identified as COVID-19 positive, they can be super spreaders even though they are asymptomatic. We can get out of this by testing everyone, but there are limitations to being able to test everyone, especially in India. We have had a shortage of test kits. There are news reports saying that is no longer the case, but I think if you want to test everybody at frequently, sort of daily or once in few days or so on, we are always going to be running behind on number of test kits. So given that we have limited testing capacity, there is very little alternative except to impose fairly severe lockdown. Given that there is such a severe lockdown, we have seen the kind of economic hardships that it has resulted in the country. So one way forward is through trying to get more results with fewer tests, and this can be achieved with various kinds of pooling schemes. I'm going to talk to you about a kind of pooling scheme that we have designed called Tapestry pooling. So Tapestry pooling allows us to get 1,000 results. So you can test 1,000 samples and give individual level results at the level of what an individual test would give you. But the number of tests you really have to do is only 100. Yeah. And this will work fine at about 1% prevalence rate, or about 10 positives out of 1,000 will be identified. If prevalence rates are somewhat different, you will see that the numbers are different. The lower the prevalence rate, the greater the gains you can make. Yeah. As opposed to the traditional ICMR pooling and other kinds of pooling that you might be familiar with, this is a single round test. So it's just one single test and it gives you the results. You don't have to go back to the sample for a second round and then do more testing. Yeah. And this gives you savings in the kits that you need to do the testing, savings in time and savings in effort. Okay. So this is sort of a one slide introduction to Tapestry pooling. Now I'll sort of go more big picture and tell you what are the options and so on. Yeah. So, Latika, how much time do I have?
Sir, it's fine. Like we have about an hour.
All right, all right. Okay, I'll try to keep it maybe to half an hour or so, so we can have some question answers after.
Sure,
Yeah.
sure, sir.
So what is pooling? Pooling means if you have n people, you collect their samples and then you put them together in one tube. You test the tube. If the test comes out negative, then the assumption is that none of them had the virus. Yeah. If the test comes out positive, then the assumption is that at least one of them had the virus. We don't know who. So a positive test result requires that you retest everybody. Yeah. So pooling really is not a single round protocol. It's a 2-round protocol, at least if done this way. So this is the 2-round simple pooling that is being done already in some countries around the world, like USA, Germany, Israel, also in India in a few states. So you pool people together. Whichever pools come out positive, you test everybody in that pool with an individual test. Yeah. So if you run the statistics for this, if about 1% are infected and there are 1,000 people to be tested, this is going to take you about 200 tests. Yeah, and it is going to take you 2 rounds of tests. In Tapestry pooling, what we do is each sample goes to 3 tests. So each sample gets tested in 3 different pools, and each pool contains, now again it's a pool, so it contains samples from many individuals. Looking at which tests are positive, which tests are negative, we can already say a lot about who is negative and who might be positive. We are going to go an extra step. We are going to numerically recover the amount of virus contributed to that pool from each sample. Yeah, and that's going to allow us to do even better than a Boolean reconstruction, and that's going to allow us to reach the numbers that I showed here. We only need about 100 tests. We only need 1 round of pooling, and we can test 1,000 people at 1% infection rates. Yeah. So we'll identify whether each individual is positive or negative. So let's look at this another way. So a more graphical way. In Tapestry pooling, if there are n individuals and there are t tests, then we have a matrix, a pooling matrix, which says for each individual, which are the tests it goes into. So those are the columns of this matrix. For each test, which are the samples that go into it, those are the rows of this matrix. And each column has 3 ones. In our scheme, each column has exactly 3 ones. So each sample participates in 3 tests. No 2 samples share more than 1 test. Yeah. So the matrix is designed in such a way that given any 2 samples, there is at most 1 test that they share. Yeah. And then we run all these tests, test 1 to test t. We look at which are the positives, which are the negatives. Whenever a test is negative, you can eliminate all the samples. Whenever the test is positive, you know there exists a positive sample. And that will already give you some hint as to who might be positive, who might be negative. But in addition, we get numerical values for the positive test. This is what the test results. So the underlying technology is something called qPCR, and that technology is going to give us some quantitative readout for how much how much positive sample was there in each test. If the test is negative, it gives you 0. If the test is positive, it gives you some level. Based on that level, we can, once suppose this is positive, then this is positive here and here. Suppose this is the only positive in this test, then we know how much positive it is. So because we know how much positive it is, it must be positive here to the same amount. We know the number here. If that is not matching here, then we know that there must be another individual in this test who is positive. Yeah. So because we are doing things quantitatively, we can get a little bit more information out of these tests. Okay.
Hello, sir.
Yeah.
Hello.
Yeah, tell me, Vijay.
Yeah, can you go to the previous slide? You mean when, let's say the first person, you have blue tick marks 2 times, it is marked actually. So you mean to that the same person is conducting, the same person is tested twice?
So same person is tested 3 times. So this picture only shows 2 ticks, but there should be 3 ticks in every column.
3 ticks means at the same time or on a 3 different time spans or?
At the same time. So the way these tests are conducted is in something called a PCR machine. It will have 96 different wells or different test tubes. So the machine can run 96 tests at once. Yeah. And so
if a person is positive, then what is the point of running more tests?
Yeah, because we are getting savings, right? I have 1,000 different samples. If I were to test each person once, I would need 1,000 tests. But now I'm only testing, much fewer, right? 100 tests. In 100 tests, right? Who is positive, who is not, by running just 100 tests. So this is a code. This is a kind of code which is I'm giving, so that just by reading which tests are positive, I can say which must be the sample that is positive. Yeah. So if a sample is positive, all the tests that it occurs in must be positive.
Yes, sir. Okay, thank you. You can continue.
Okay, so saying this in words, every sample is tested multiple times in multiple pools for us, right? The quantitative viral load, the amount of virus in each pool is reconstructed. So think of that as a vector y1, y2, ym, yeah, column vector. The viral load of each sample is unknown. This is what we want to reconstruct, x1, x2, xn. Okay, m is the number of tests, n is the number of samples. So we set this up as a system of matrix equations, a times x equals y. Then a is our pooling matrix, 1, 0 matrix, yeah, which sample goes into which well, yeah. Now we want to solve this system of linear equations. Is that m is much smaller than n. M is like 100, n is like 1000, right? So this matrix is very short and wide. So solving a matrix that is short and wide, you cannot invert, right? There are many solutions. There isn't a unique solution. So what do we do? Are we stuck here? So we have assumption here. The assumption is sparsity. Find the sparse vector. Why is this justified? Because typically, most tests that we do for COVID-19 are negative. Yeah. Even today, about 4% are positive. Most people are negative. And because of this, we should be looking for sparse solutions to these equations. As soon as we start asking for sparse solutions, it turns out that there are some very clever algorithms that can actually solve equations precisely. Okay. There is an entire well-developed field within signal processing and statistics, which goes by various names: compressed sensing. It's also called, ridge regression, lasso. There are many names. Yeah, bunch of related techniques. And the idea there is that you want to take the difference ax minus y, take the sum of the absolute values of that vector. Ax minus y is a vector. Take the sum of the absolute values. Yeah. Now treat that like a loss function or an error. Yeah. And you want to try to minimize that. When you try to minimize that, it turns out that you end up finding a sparse solution. So that is really how one does this. Of course, we have some peculiarities in our particular problem formulation, because of which we move away from those algorithms, we adapt them to our own purposes, and we do things fairly differently. But that's the starting place. That's where we started from. Okay, so let's do a comparison first conceptually and then with numbers. So conceptually, simple pooling is great. Simple pooling tells us, if you put 5 samples in a pool, in 2 rounds, you can know which individual is positive, which individual is negative, and it works about as well as ordinary testing. It will conserve RNA extraction and testing kits because 1,000 can be tested tests. It's already deployed in the field, so it's fairly well established by now. And the amount of liquid handling you need to do, amount of pipetting you need to do, is about the same as you need to do for individual testing, slightly more, appreciably so. Okay. The problem with simple pooling, which is one reason why it has as popular as one would want it to be, is that PCR is a slow test. Okay, at least as commonly done in the field. It can be done faster. Some people do it in 15 minutes, 1 hour, and so on. But the traditional PCR is a 4-hour test, and that's the one most widely available in most labs across our country. And it is fairly, lots of steps. You need to do RNA extraction. You need to load the PCR machine, let that run. It takes like half a day to do 1 round of PCR. If you have to do 2 rounds of PCR, your entire day is gone. And then the second round, when you have to go back to the original samples. You have to again extract them. You have to again extract RNA. And going to samples means you have to wear personal protective equipment. You have to again wear the suits and the masks and the gloves. and that's not pleasant. People feel, okay, I'm saving a few tests, but the trouble is too much. Like your entire day is gone. So they would rather just do it in one shot and end up using more kits. Yeah. So this has been a big disadvantage of pooling. Even conserves things and so on. Okay. How does Tapestry pooling compare? These remain true. We still tell which is positive, which is negative. We conserve kits. We conserve a bit more, at least twice. We take about half the test that simple pooling requires empirically. We are not yet deployed. We are still in clinical trials. And the amount of pipetting becomes more, as you will see, because we have to pipette each sample 2 to 3 times. So the amount of pipetting times increases by about a factor of 3. Yeah. But there are some other advantages that come with it. So with Tapestry, we can choose the coding matrix in a way that is tuned to whatever prevalence rate we expect in the population. So if we expect about 1% to be positive, we can design for that. If we expect about 10% to be positive, we can for that. So that huge dynamic range is there, which is not there with simple pooling. Simple pooling works at around 6-7%. At less than that, it works. It gives you sort of a maximum gain of about 4 times or so, 5 times, and that's it. That's the range. Tapestry give me lower prevalence rates. We keep giving you better and better gains. And we can work at 10%, 12% prevalence rates. We reconstruct viral load. So we don't just tell you which sample is positive and negative. We tell you how much it is positive by, and we do it in a single round. And each sample is tested thrice, so you're unlikely to miss it all 3 times. So we have a same or better false negative rate, in fact, than single testing. And we have a lot of sort of statistical control over when we call something as positive or negative, how well can we do it, and by increasing, decreasing the number of tests, we can make it suitable for various different use cases. If it's a clinical setting, positive or false negative, we can tune to that. If it's a screening setting where you want to test a large number of people and you're okay with some false positives, you don't want any false negative, then we can tune it like that, yeah, with more gains. And yeah, so that's the idea. Okay, here are some numbers. So with Tapestry pooling, we can do 70 samples in 21 tests at about 6% prevalence rate, 200 samples in 45 tests at about 4%, 400 samples in 63 tests at about 2.5% prevalence rate, about 1,000 samples in 90 tests at 1% prevalence rate. Yeah? And we have done some experiments. So this was the very first experiment we ran. This was at NCBS, samples into 16 pools. Tested these 16 pools, gave us back that vector of quantitative readings of these 16 tests, and from these we were correctly able to identify which was positive, which was negative. They repeated this experiment with 0 positives. Of course, we said everything is negative. With 1 positive, we found the 1 positive, we said everything else is negative. 2 positives, we found the 2 positives, we said everything else is negative. And yeah, so this works. Yeah. Another experiment was tried at Harvard, where 64 samples were put into 24 pools. And I think this had 3 positives, not 0, 1, 2. This had 3 positives. Again, they gave us these 24 test results, and we were able to say which 3 samples are positive. And we were able to get all 64 samples right. More recently at Harvard, they put 120 samples into 40 tests according to our matrix. And again, 3 positives. We correctly identified all 3. 1140 samples in 90 tests with 11 positives. And our algorithm at that point, current algorithm, also gets this right. It gets 11 positives and everything else negative. So it gets all 1140 samples right. Yeah? And this meant, you might imagine that this is a lot of samples, right? More than 1,000 samples. And that means more than 3,000 pipettings. It might take a long time to pipette. This was done with a liquid handling robot, and with the robot, it just takes like 18 minutes of pipetting to handle all these samples. So this is a message that if we can get access to liquid handling robots, we can really deploy Tapestry pooling kind of ideas at many places and do a lot of testing in very little time. Yeah. So I won't go into some of these. I can save this for discussions. Yeah. So we are in clinical trials right now. Some more tests are going on with COVID-19 samples. which were actually received in the field and so on. And okay, so yeah, so what are the use cases? So one use case is in a clinical setting where traditional labs who are testing, if they are seeing fairly low rates among some subset of the population, then they can try to use Tapestry, up to 10% infection rate. They can try to use Tapestry pooling and get some savings. Another use case is, test hospital staff, people who work at hospitals, test them daily. Okay, if you're testing them daily, then chances are most of them will be negative. Test CISF guards at airport daily, test police personnel, test delivery personnel, so on, right? High risk population who can be tested every day and need to be tested every day. So these kind of use cases can also be done. So even fairly large hospitals, neighborhoods, passengers arriving at airports can be tested. Yeah, so I think that's the big picture. And we have built an Android app. So you might imagine, how would the person doing the experiment know how to pipette? So our app tells them how to pipette. And then how does the person running the experiment know how to solve? They enter the test results they got into our app, and our app solves it for them and tells them what would have been the results if they had run individually. Okay, so that is yeah, so that is it. This work started at IIT Bombay. Sabya is my PhD student. Ajit is in faculty member in computer science. Aditya, Vidya, Ronak and others were at shop101.com and they helped us build the phone app. Das and his students did many of the experiments. At the WIS Institute, Tom mostly did the experiments. And yeah, so that's it. Yeah, I'll take questions.
Okay, thank you so much, sir. So now, I guess we have some general questions, so we'll start with that, and then we can take the questions from the audience also. So, if you all have any questions, please put them in the chat box. Yes, sir. So other than that, I think the first question that we all have, or is that like, when did you start working on this project, or like, how did you come with this idea, basically?
Yeah, so this idea actually came to me. So I before I came to IIT Bombay, I was at TIFR, and this was, I think, during a previous SARS epidemic or something like that. So at that point, I had this idea of doing compressed sensing for PCR and trying to do the testing of large number of people with few tests. At that point, I think the nature of that infection was that 10% people were positive, and there were few asymptomatics. If you had the infection, you exhibited symptoms from like day one. So somehow the clinical case for this was not so compelling, because everybody is symptomatic. It's easy enough, you don't have to test people to know whether they are infected or not. You just see if they have symptoms. So at that time, I didn't get much interest from experimentalists in wanting to try out these kind of ideas. Now, when this COVID-19 happened, it turned out to be a good use case for those ideas. So those ideas kind of came back to life. And in this case, fortunately, I managed to interest a few experimentalists in taking this forward. And my PhD student could quickly, code up something that worked. And that's how, it started.
Okay, right, sir. So now, at what stage this project is in? Like, has it been put to use, or is it being used for pooling samples?
Clinical trials, we are not allowed to use it in the field right now, because there is an appropriate, regulation and all that has to be done. We have to get appropriate permission before this can be used in the field. But initial tests have been promising, and we've been getting, sort of whatever is positive and whatever is negative, we've been getting things right. So we are fairly optimistic about this getting the required permissions, and we are working towards.
Okay. So from the audience, we have two or three questions. So I'll just start with those. So the first question is that, like, can you throw some light on the current testing methodologies that are being used in India?
Okay. So yeah, I mean, I don't know how much light I can put on current testing methodologies. Okay. So I mean, basically there is PCR testing and there is antibody testing. I think maybe some of you here maybe know more about this than I do. So antibody testing looks for proteins. PCR testing looks for RNA. Uh, yeah, with the sequence of the virus. Yeah. Now, the protein is created by our body. It's called an antibody, right? So the virus is called an antigen. So protein is something from our body that recognizes the shape of the virus. So obviously this does not happen from day one. The body takes a few days before it develops what is called an immune response to the virus. And when that immune response happens, we get proteins that sort of stick to the virus and then do something about it. So an antibody test tries to see if there are such proteins. Yeah. And recent research suggests that for COVID, antibody tests start giving positive some 20 days after infection. Okay. So antibody tests really don't catch early infection, but they are a very good indicator that this person was infected in the past. They remain for like 3 months or so after the infection. Yeah. So if you had infection today, then till 3 months or so later, you will have that antibody, and so people will know that you had the infection. PCR is it can pick up the infection sort of to some sensitivity day 1, much greater sensitivity day 2, 3, and so on. So it picks up the infection if you have it. So PCR is really the test. So it's called a gold standard because it's the most accurate test we have. If there is even a single molecule in the pot, PCR picks it up. If there is no molecule, PCR doesn't pick it up. It's a super sensitive, super specific test. And errors that happen in testing usually don't happen because of PCR, they happen because of sample collection. So what PCR does is it uses a naturally occurring enzyme called polymerase. So polymerase is this magical molecule which can, so given a strand of DNA, so I hope all of you know that DNA is a polymer, which means it's made up of 4 types of monomers, A, T, G, and C. So a strand of DNA is really a sequence, right? It's a string from this alphabet of 4 characters, A, T, G, C. Yeah. So given a strand of DNA and given a short complementary region. So what does complementary mean? DNA again has this property that A sticks to T, G sticks to C. So you have a short complementary region. This is called a primer. So it's supposed to match something in the virus, right? Some sequence in the viral genome. So given that, the polymerase comes and sits on that double-stranded region, and then it starts extending the DNA. So polymerase is this magical molecule which copies, right? It's a copying machine. It's a Xerox machine, yeah, for this string. So it copies this string, and then your PCR machine raises the temperature. So what was now double-stranded separates into 2 single strands. Right. It lowers the temperature. Again, in these single strands, you get the primer coming and sticking, forming a place for polymerase to sit, and then polymerase again starts extending. You again get now 2 double strands. When you heat, you get 4 single strands. When you cool, you again get 4 double strands. When you heat, you get 8 single strands, and so on. So in every cycle of heating and cooling, the number of strands of DNA doubles. Okay, and doubling like this means it's exponential growth. You all know this story of the person who went to, the king's court, and he had invented this game of shatranj or chess, and the king said, "How should I reward you?" He said, "For every square on this board, for the first square, give me 1 grain of rice. For the next square, give me double of that. For the next square, give me double of that," and so on. Right? And the king realized that he would run out of rice. He didn't have enough to cover all 64 squares. So that's exponential growth for you. The same thing happens with PCR. The number of molecules start growing exponentially, and at some point you run out of the resources needed to do that exponential growth, and so it saturates, and you get the growth. So it saturates into a sigmoid curve. Yeah. So yeah, so that's PCR, and there are antibody tests. These are the two kinds of tests mostly going on.
Okay. And another question we have is that the uncertainty rates, as you said, like you showed the data. So in that, the question is that does a large uncertainty in prevalence rate create any difficulties, or is it manageable, or is that much error like
Let
allowable?
us hit on it. I was hoping somebody would ask. So good. Yeah. So let me bring up that slide. Here it is. Is it visible?
Yes, sir.
Okay. Yeah. So what does our algorithm return? Our algorithm returns 3 categories: positive, negative, and undetermined. Okay. So most runs, at least all the runs we have done so far in the lab, we get only the 2 categories, positive and negative. So every sample, we tell you what it is, right? We don't have undetermined. But if there are unexpectedly many positives, right? So we guessed that the prevalence rate is 5%, but it turned out to be 10%. Okay. So in that case, we have more positives than we have designed for. Okay. In that case, we will have some samples in the last category. We will still be able to tell you many samples. If there are 5 positives, we may return 10 undetermined. Okay. But we'll still tell you everything else, right? 90 of them are negative for sure. Out of these 10 undetermined, 5 are positive. We will also tell you that. We will not know which 5 are positive. We may, in addition, also be able to give you some confirmed positives, but usually that number will also decrease as we switch, right? So in this literature, in this scientific literature, this problem is called group testing problem. How do you test a group with a few tests? Okay, in group testing, there are these 2 worlds. So there is this world of single round testing. So single round is called non-adaptive because you don't adapt to the test results. Your test is designed once and for all, irrespective of what the test results come out to be. Yeah. The other world is adaptive. The adaptive world is you do one sample test based on how, or one pool test based on how that pool come out. You test the next pool based on how that pool came out. You test the next pool and so on. For PCR, then we solve it for them. We give them the results. So as far as their end is concerned, the only new step is the pooling. Yeah. And they're already doing pooling for simple pooling, but now we tell them how to pool. That's all.
Okay. Right. So, okay. So, like, are there any further improvements in this that are possible, or are there any further plans do you have for this?
That's a great question. So the thing is that this is, we have complicated things, right? Things were simple. You test one sample with one test, or 5 samples in one pool, and you test and then test everything in that pool if positive. That was simple. Now we have complicated. We have some kind of a code and everything is coming together. But that complication has its payoffs. So one payoff is that suppose we have multiple samples that belong to people from the same family. Suppose we have samples where we have some indication that they are more likely to be positive, some are less likely to be positive. So we have all this kind of side information. We know who met whom, right? We have a network of social connections. So we can do inference with all this information, and we can come up with a prior distribution for who is positive, how likely they are to be positive. And then we can interpret our test as doing Bayesian inference, going from a prior to a posterior. And that can really, go much further than what we have shown. We have taken this completely worst case where we don't know anything about anyone. We are working with our
Yeah, so if anybody has any other questions, we can have them, I guess. Other than that, so like, are you also working on something else related to COVID-19, or do you have other plans also?
So I mean, I can show you some of. Okay, so I'll tell you one thing maybe that might be of interest to you. That what we have put out, right? So we have. So I'll just share the website with you on the chat box.
Okay.
Yeah, so that's our website. So if you go to our website, there is a GitHub, there is some code there, and you can fork the GitHub. clone it, and you can just start working on it. You can try out your own algorithm you want. If you want, you can try out your own matrix if you want. So that's one way to get involved. More recently we've been looking at more Bayesian directions and trying to see if we can build Bayesian solvers for this.
Okay. Yes, so like all of you can check out this website in the chat box. Other than that, if anybody has any questions, you can post, or then I guess we can end this. Okay, okay, sir. Thank you so much for joining us for this webinar and giving us this insight into your project. And also thank you for joining this webinar. Another thing, if you have missed any part of this talk, we will be sharing this YouTube channel, WnCC's YouTube channel. So we'll be sharing this webinar video on that also. So if you have missed, or if you want to go through again some part, you can visit our YouTube channel.
Great. Yeah.
Yes. Thank you so much, sir, again.
Yeah. Thank you.